Okay, so this is a brief introduction to the idea that climate engineering, geoengineering will require a different set of indicators as opposed to the global warming indicators that we are so used to, which obviously is completely dominated by the global mean surface temperature. We keep looking at the global mean and the maps, and we keep debating about whether the global mean actually means something for regions and local impacts, and what the patterns of warming mean. As we have seen, we have polar amplification, tropics are already warm, not warming as much, but the North Atlantic, where the deep water forms, is not warming or maybe even cooling, but in the future it will continue to cool less, and so on. So this is of interest for climate scientists in terms of understanding the physics, thermodynamic response, dynamic response, coupled ecosystems. So the idea is then extended by projected warming and precipitation changes to how forests will respond, how crop yields are affected, how human health is affected, and maybe even look at how GDP is affected, as we did before, by using econometric models combined with the representative concentration pathways. And there are also shared socioeconomic pathways which are combined with sustainability scenarios and policy choices and so on. But do those indices actually work for climate engineering? It turns out that not so straightforward. So let's start with this one of just looking at global mean surface temperature, which is shown here in the red line from an observed data set HADCRUT 4.3, going from the 1800s to the 2010 or so, here 2014, and it is showing the Central England temperature, again from a data set HAD-CET, Central England temperature. And the point made here is that if you just look at the relation between global mean temperature over this period versus annual temperatures over Central England, you have a fairly significant correlation, but it's at 0.51. If you take decadal smoothed time series of Central England temperature, the correlation between global mean surface temperature and Central England goes up to 0.87, which is pretty remarkable, even though statistically you have to remember that every time you smooth a time series, you're going to reduce the degrees of independence. And if you take a multi-decadal component, it's almost 1 at 0.96, which means Central England is basically following a global warming signature pretty closely. Okay, that's good. That tells you a lot about how global warming is affecting the temperature over Central England. But what does it mean in terms of precipitation? So if you look at anomalies in Kelvin again, or millimeters per day of rainfall, so then you look at the same surface temperature time series from here, and you look at Central England precipitation during its rainy season in June, July, August. Okay, so at the annual time scale, the two are basically have no correlation, 0. And at decadal time scale, the correlation is still 0. And multi-decadal time scale, you begin to get some signal that the two are correlated at minus 0.48, which means global warming is going to reduce the rainfall over Central England. This tells you that the correlations in the Earth system are complicated, and the index we use for global warming, like global mean surface temperature, global mean sea level rise. Of course, we always track the emissions, either in terms of CO2, which is easy to measure, or CO2 equivalent, which should combine methane, nitrous oxide, HFCs, etc. together with CO2. And people look at derived quantities, Arctic ice, Antarctic ice, monsoon changes, and so on and so forth. So what should we do for climate engineering? here is a good summary of the things. The results of literature survey of climate engineering studies investigating solar radiation management, SRM, terrestrial carbon dioxide removal, CDR, and marine carbon dioxide removal. Studies that investigate various methods are shown in gray. The size of each circle refers to the number of studies that used the respective indicator, ranging from 3 for sea level to 64 for surface air temperature. So it gives you a sense of people's favorite index or their focus. Colors indicate the relative proportion of the studies referring to the specific classes of climate engineering method. Indicators are located approximately in the physical space they refer to. So we are looking at solar radiation management in yellow, marine carbon dioxide removal in this blue color, and terrestrial carbon dioxide removal in the green color. And then there are studies that compared multiple geoengineering methods. They are included as well here, for example. So there are many who have used vegetation, NPP, as indicators, evapotranspiration, atmospheric physics, carbon flux, atmosphere to land carbon flux, soil processes, albedo changes, atmospheric to ocean carbon flux, carbon budget. Surface air temperature is obviously the largest metric used by geoengineering studies. Energy balance, which is always critical, atmospheric chemistry, precipitation, sea ice. People have focused on the impact of climate engineering on sea ice, on ocean temperature, ocean biogeochemistry. Acidification, alkalinity have always remained of great interest, especially for studies that do marine carbon dioxide removal, as you can imagine. And there are those that have used atmospheric CO2 and surface PCO2, so split between carbon type removal, so land CDR and ocean CDR, but even for some intercomparisons and solar radiation management, ocean acidification, ocean primary productivity, and ocean physics. The main thing to remember is that when we do things like solar radiation management, we are not removing the emissions, we are just reducing the energy coming in. So the carbon dioxide is still being emitted, it's not being removed in the solar radiation management, and various other scenarios of RCP 8, 8.5, 2.6, 4, 6.5, etc. are being used in combination with SRM. So there are various ways to do it. You do a solar radiation management and see what happens if you suddenly stop it, because carbon is not being removed, you're just managing the energy coming in. So acidification and other impacts of carbon dioxide will still be going on, and if you suddenly stop solar radiation management, everything is going to jump because all the carbon dioxide in the system is still there. So these are the kind of things we have to worry about, because the relations between various quantities like temperature and precipitation and other Earth system indicators like vegetation, agricultural productivity, health impacts, sea level rise, ocean acidification, etc. the correlations are going to change in just the RCP representative concentration pathway scenarios versus when you add these climate engineering aspects on top of the scenarios for where the emissions are headed. And the RCPs themselves, of course, include renewable energy, population, science and technology, policies, carbon capture and sequestration, and so on and so forth. Bioenergy and carbon capture and sequestration, called BECCS, and so on. So the whole idea of worrying about indicators or metrics for climate engineering is to remember that just the indicators for uh, global warming, which may extend to economic impacts, as we saw in the previous one about whether geoengineering will affect equality and GDPs and so on. Without geoengineering as well, we look at impacts on GDPs, health, mortality, morbidity, productivity, and so on. But you also have to worry about the competition between multiple goals or different goals. So this is looks like a complicated figure, but basically it's looking at maximum rate of temperature change versus maximum sea level rise in meters. So this is Kelvin per year, this is meters, and the green dot here is the representative of the observations between 1980 and 2009 in terms of the rate of temperature change. It's not the total change since industrial revolution, so you have to be careful at what rate global warming was happening over this period versus at what rate sea level rise was happening, what was the maximum rate of that. So this figure is complicated, but basically it's showing that depending on whether the abatement strategies are following RCPs and looking at mitigation scenarios, or whether geoengineering strategies are being used, and how often the forcings are being applied, every 5 years and longer. So this continuous forcing with the phase out of every 5 years, and the polygon here covers the range. Let me make sure I say this right. The lower and upper line of points here show continuous and discontinuous forcing. So this is the continuous forcing, this is a discontinuous forcing with phase out of 5 years. As I said, phase out time of 5 years. People always worry how to apply geoengineering. Should we use it as a way to delay global warming so that we can stay on the path to 2 degrees C warming with 66% probability, or 1.5 degrees C warming? So turn it on and off, or whether it's going to stay on continuously, and so on. But the main point of this figure is that depending on whether you are trying to reduce the hazards due to sea level rise, or you are trying to reduce hazards due to rate of temperature change, you may have contradictory impacts on each other. So trying to reduce hazards due to temperature change may not necessarily give you a reduction in hazards due to sea level rise, and vice versa. Okay, so this is tricky, which basically brings us to the point of how would you design the indicators and metrics for climate engineering in addition to global warming. So the bottom-up approach is still considered to look at how geoengineering affects temperature, precipitation, sea level rise, and related things like GDP, GDP distribution, GDP share of global GDP, and so on, that we discussed before, versus a top-down approach where the decision makers say, we want geoengineering to maximize, let's say, food production, or minimize sea level rise, or some other indicator, maximize GDPs, maximize productivity, whatever. So some other indicator, and then you percolate that down into the scenarios using econometric models, climate models, integrated assessment models, whatever you have at your disposal to drive geoengineering. Neither one is perfect, and this paper that we are looking at mainly for this purpose advises an iterative process where the bottom-up and top-down metrics are iterated based on the goals to make sure that the conflicts between different goals is not too severe. And include stakeholders, climate modelers, academia, societies, and whoever else, all the stakeholders. Okay, so sounds nice, but actually doing it obviously is going to be complicated. But nonetheless, combining this with the previous podcast, you can understand that geoengineering is going to come with lots of ethical questions about who pays the price, what happens with the unintended consequences, and so on. Because once you do geoengineering, whether it's solar radiation management or carbon dioxide removal, the unintended impacts are not really unintended anymore. You cannot call them unintended consequences, because you went in knowing that there are going to be consequences that you didn't completely know would happen. So, and there will be disparities. If you do solar radiation management over the US, and if it ends up reducing precipitation over China, obviously this is a problem. So all these kinds of issues are related, but nonetheless the main point is that we need indicators for climate engineering and metrics to make sure that we are doing mostly what we intend to do in terms of geoengineering. Okay.